Welcome to Lecture 1.3, Constructing Truth Tables from Compound Propositional Forms. The objectives of this lecture is for you to learn how to convert compound propositions into their correct propositional form, and second, to construct the corresponding truth table for the propositional form. Here we will discuss how to create truth tables for propositions. Just like in algebra, wherein we follow the PEMDAS, parentheses, exponents, multiplication, division, addition, and subtraction, in order. In logic, we also have the precedence of logical operators. First, whatever inside the grouping symbols like parentheses must be performed first, followed by negation, conjunction, disjunction, implication, and last, the biconditional. Suppose that we have here a compound proposition. The negation of P or Q and R implies P if and only if Q. How will we do this? So first, we are going to perform first what is inside the parenthesis. And inside is a combination of disjunction and conjunction. So by the precedence of logical operators, the conjunction will go first, Q and R. And then Q and R will be counted as one unit, and it will be combined using disjunction with P. And then it will be counted as a single unit, and then we will negate that. So we have the negation of the entirety, and then counted as one. We will now involve this with the implication. This becomes the color orange. It is now counted as one, and then it will be paired via the biconditional operator. This is the equivalent of our original statement. Express the following statements into propositional forms using propositional variables and logical connectives. Construct the truth table after. So let's have the first example. Neither 1 nor 1.2 is an integer. Since we don't have a specific equivalent form for this of neither nor in the symbols, we can express this as 1 is not an integer and 1.2 is not an integer. So they are the same. Now, we can express our P and Q as P, 1 is an integer, and then Q, 1.2 is an integer. So always remember that whenever we are trying to represent a proposition using variables, P and Q must be positive. So we drop the not so that we can reserve that for the negation. Next, the structure of our original statement is not P and not R. This is now the truth table for that. First, P is true. 1 is an integer, yes. Q, 1.2 is an integer, that is false because 1.2 is not an integer. Next, we negate P and Q. So we have not P is false and then not Q is true. Now, when we combine them together using conjunction, the original statement is false. Neither 1 nor 1.2 is an integer is false. So this is how we do a truth table for compound propositional form. So the first thing that you're going to do is to get the correct structure so that you can get the correct truth value. Next, if violet is a color in the rainbow or red is not a secondary color, then violet is a color in the rainbow and red is a secondary color. Take note that this sentence is a little bit redundant in some ways, but let's see, how will we transform this into propositional form? First, P, violet is a color in the rainbow. Q, red is a secondary color. Okay, let us now have the structure. We have here P or not Q implies P and Q. Take a look at the original statement. We have there an implication. And then the premise is a disjunction. And then our conclusion is a conjunction. Okay, next, let us create the truth table. First, we have P, Q, and not Q because those are what we need. You no longer have to get not P because that is not needed in our overall structure. P, that is true. Violet is a color in the rainbow. And then Q is false because red is a primary color. Now we need not Q. Not Q is true. Next, we have the P or not Q. P or not Q, both true. So that will be true. And then P and Q, true and false, that will be false. Now, when we combine them together to form an implication, true implies false will be false. Example 3. Velocity is a vector quantity if and only if speed is a scalar quantity or distance is a vector quantity. We see the keywords here, if and only if, and then the or. Now, P, velocity is a vector quantity. Q, speed is a scalar quantity. And we have R, distance is a vector quantity. The structure of our statement will be P, if and only if, Q, or R. Next, let's have the truth table for P, Q, and R. Okay, for P, that is true. Vector is indeed a vector quantity. Q is speed is a scalar quantity. That is true. And then distance is a vector quantity. That is false because that is a scalar. For our biconditional statement, we need to get the truth value of Q or R. Q or R, true or false, that will be true. Now, connecting them together using the biconditional connective, we have true, if and only if true, so that will be true. So our example 3 is logically true. Example 4, Japan is in North America or Russia is in South America if my birthday falls on a Tuesday. Okay, again, always remember that logic only cares about the truth values of the statements, regardless on how we will interpret them as people or as human beings. All right. Here, let us rearrange the statement. If my birthday falls on a Tuesday, then the then is invisible. Japan is in North America or Russia is in South America. P, my birthday falls on a Tuesday. Q, Japan is in North America. And then R, Russia is in South America. Let us now create the truth table for P, Q, and R. The structure will be P implies Q or R. So this is the same as the previous example. For P, that will be true or false because when we say my birthday falls on a Tuesday, for example, you don't know me, so that will be arbitrary. There will be two possible scenarios, whether it's true or false. And then for the Q, Japan is in North America, that is false. And then for R, that is also false because Russia is not in South America. Next, the required will be Q or R. Since both Q and R are false, Q or R will be false as well. And then next, P implies Q or R. To take a look at the yellow colored cells, true implies false will be false, and then false implies false will be true. So there will be two possible combinations for this. First, when P is true and when P is false. Those will yield different truth values for the entire statement. Example 5. It is not the case that both sine pi over 2 is greater than 1 and a hexagon has 5 sides. Okay, this one is a little bit different because this one, this sentence is started by, it is not the case that, and then followed by both blank and blank. So meaning to say, we are trying to negate a conjunction here. First, let us have the representation. P sine pi over 2 is greater than 1, and then our Q hexagon has 5 sides. Again, we are negating a conjunction, so it means that the structure will be not P and Q. Let us now have the truth table for this. Our P is false because sine pi over 2 is equal to 1. And then Q is also false because a hexagon has 6 sides. Now, when we combine them together to form a conjunction, that would be false. And then when we negate the entire conjunction, that would be true. So the statement, it is not the case that both sine pi over 2 is greater than 1 and a hexagon has 5 sides is logically true. You have now reached the end of this discussion. You are highly encouraged to answer exercise 1.3.